Healthy and Thriving Communities SSN seminar on using systems thinking in environmental and societal challenges. My name is Miranda Blake, and I am the co-stream lead along with Georgie Russell. The Science and Society Network was formed in 2018 in recognition that scientists and humanities and social scientists need to work together to meet the great challenges of this century. No single academic field can bring about the changes we need to see in the world. Bridging disciplinary divides is the key to finding new solutions to the problems that we all face. So SSN supports early and mid-career researchers across the university who are embarking on groundbreaking interdisciplinary grants and projects. I'd like to begin by acknowledging and paying my respects to traditional owners of the lands on which each of us are on today. Here, that's the land of the Wurundjeri people of the Kulin Nation. And I'd like to pay my respects to their elders, past, present, and emerging. Let us pause to learn, to acknowledge, and to celebrate their ancient histories and cultures. For those of you who have not attended one of our seminars before, a quick rundown on what will happen today. So I'll introduce Professor Birgit Kopainsky, and Birgit will present for around 40 minutes or so, and then we'll have some discussion comments. We've got Associate Professor Jennifer Brown and Dr. Tari Forrester-Bowling here. And then we'll throw to general questions from the audience here in person and also Q&As online. So I'll be chairing this discussion here in person and on Zoom. And my colleague, Karina Traits, will be moderating the YouTube live chat. So really keen to hear and answer your questions today. So you can either, again, post those questions into the YouTube chat, or you can email to ssn-info @deakin.edu.au. And if you are tweeting about this, or maybe you're on LinkedIn, we have a hashtag SSN seminar. So I'd like to introduce Professor Birgit Kopainsky. She's a professor in system dynamics at the University of Bergen and the director of the System Dynamics Group. She holds a PhD in agricultural economics from ETH Zurich and a master's degree in geography and environmental sciences from the University of Zurich. Her research explores the role that system dynamics can play in facilitating transformation in sociological systems, such as transformation towards sustainable and resilient agri-food systems. She uses system dynamic simulation models to explore economic, social, and environmental conditions and resource use, so assessing the effectiveness of proposed management and policy actions. She also facilitates participatory modelling processes that help to integrate science-based knowledge and local knowledge so that stakeholders at different levels are better able to continuously test, learn, and develop knowledge and understanding in order to cope with change and uncertainty, which is a very challenging but noble goal. She conducts and supervises research both in Europe and in the Global South and works with diverse stakeholders at local, national, international level. We're very privileged to have her here as a visiting thinker in residence at Deakin. She's been the principal investigator or co-principal investigator in large interdisciplinary projects that has received large funding from a broad range of resources. Thank you very much, Birgit.
Yay. I sure hope this will work. Well, thank you very much, Miranda, for introducing me, and thank you everybody for having me. It's a great pleasure to talk about so many things that are so close to my heart. So I have a very packed agenda for you today because I want you to share in my passion for systems thinking and modeling, interdisciplinary work, and give you a little bit of a sneak peek at kind of food system related research that we've been involved in the last couple of years. So I'm going to start with setting the scene a little here in the title. It's maybe a little broad, using systems thinking in environmental, social, societal challenges. I will focus on food systems, allowing myself to talk about something that I know, because my time here at Deakin has exposed me very much to public health issues that I'm still grappling with and trying to get into. This I feel comfortable talking about. So let's, and it works. So food systems, what are we talking about here? We're talking about systems where we're maybe interested in specific so-called food system outcomes that can be related to food provision, but also to social and environmental welfare. But these food system outcomes, they don't happen in isolation. They're on the one hand a result or an outcome of food system activities, but they also have consequences on the larger system surrounding these food system activities, like socioeconomic drivers, global environmental change drivers. And these, in turn, come back and affect the way we produce food, the way we process food, the way we distribute food, and the way we consume food. So this is pretty much the epitome of a complex problem. And what happens in complex systems, everybody has their own pet theory of what will help finally solve the problem. And those can be solutions targeting climate change, energy, or natural resource management. They can be solutions targeting food production and supply, poverty alleviation, human health and nutrition, domestic market organization, food security, consumption, and demand policies. Who is right? Do we know who is right? Well, we don't, right? Because what happens in these why are you not seeing this? What happens in these complex systems is that we see feedback loops that connect the larger subsystems, but also the smaller systems within the subsystems, and that makes for a very that makes it difficult for us to anticipate what the consequences of well-intended interventions are. And that's really my everyday life as a system dynamics researcher. I am interested in how we can use the tools that systems thinking and system modeling has to offer to support transformation processes in systems, in complex dynamic systems, such as food systems. So, assuming that not everybody has an elevator pitch ready for what system dynamics is, and those of you who have know that the elevator needs to go really slowly for you to be able to explain the approach. I'm going to start with giving you my take on what system dynamics is, and really one of the reasons why I'm so passionate about this method is that I think it's a very helpful approach to support interdisciplinary work that is necessary for addressing some of the grand environmental and social challenges that we're facing. So system dynamics, for me, if I'm pressed to define it, is a happy marriage of systems thinking and computer simulation modeling. Where systems thinking is more covers more the qualitative end, where we ask questions about what important drivers of an observed problem are, how these drivers are connected to each other, how we can make sense of these interconnections, what kind of stories these interconnections tell us. And then we marry this more qualitative end of the approach with computer simulation modeling, where we translate some of these interconnections into mathematical equations. I'm going to show you an equation at the end. And those of you who are taking my quantitative seminar, they know that these equations are less scary than they sound. So we translate them into mathematical equations so that we can formalize the relationships that we identified and start investigate how the system has behaved in the past and how it might behave in the future as a result of the drivers and their interconnections that we identified in the qualitative end. And I'm going to show you examples of how we do that. And after showing you some examples, we'll go into more detail. I'll come back to the approach and summarize the steps that we go through when we build these models, analyze these models, and use these models for learning about how to dance with systems. I don't want to say learn how to manage these systems. You can't manage complex problems. You can dance with them, and I think that's very important, right? So what are some of the key features of the system dynamics approach? I would say feedback thinking is probably the one key defining feature. As we're doing modeling and simulation, a lot of it is we share with other approaches, but really the focus on feedback loops and on this mantra that a set of feedback loops, which we call the structure of our system, is what drives the behavior of the system. It's what determines the behavior of the system, so the development of key performance indicators over time. And we'll come back to this. So it's really feedback thinking structure. For the quantitative end, we need to identify stocks and flows. We use modeling and simulation, and we do all of this not because it's so much fun. It is fun, but we do build models because we want to understand what causes problematic behavior, and we want to experiment with the model how we can alleviate problematic behavior, how we can minimize trade-offs between important system outcomes, etc. This sounds all very mysterious, right? That's why I'm going to give you 2 examples. And I chose those examples to illustrate a little bit the breadth of the approach. One is more on a global level, and one is more on a local level. And I hope you get a bit of an insight of the kinds of questions that we can analyze with this approach, but also the kinds of things that we can't do. And I'll get back to that towards the end too. So let me jump into case study 1, which is which is based on a still ongoing EU project and essentially led by my PhD candidate Jefferson Raja, who deserves all the credit. I take all the criticism. But it's no, I mean, it's the everyday life of research. Research is done by PhD candidates, right? Us senior researchers, maybe we have sometimes we have ideas, sometimes we have advice, but they carry the load, and I really want to acknowledge that. So this is a mouthful. This case study has so far been published in one paper that really doesn't have the most intuitive title I recognize, an endogenous modeling framework of dietary behavioral change in the fully coupled, I can't even say that in one breath, human climate Frida version 2.1 model. Let's unpack this a little. So the case study is grounded in the observation that, and we know that, all of us know that emissions have increased massively in the past decades, and we're still going strong. One of the among the high impact private behaviors are meat consumption, transportation, and electricity use. And I'm going to focus on meat consumption in this case study, with work on transportation and electricity use being underway and following later on. So why are we talking about meat consumption? We're talking about meat consumption because meat consumption globally has increased a lot in the past decades, both in absolute terms on the left-hand side of the slide, where we see the global meat consumption, but also in terms of per capita consumption, which we see on the right-hand side of the slide. So it's not just meat is not being consumed more because we have more people. It's also that everybody on average consumes more. And is that a lot? Is 40 kilograms per capita per year a lot? Probably depends on the benchmark or on the goal value. But if we take a goal value that recognizes environmental health but also human health, it is a lot. The kind of safe space for per capita meat consumption is much lower, as defined by the Planetary Health Diet. So there's a lot to be gained in terms of emissions, if only we could curb meat consumption. Right? And that's also recognized by the Intergovernmental Panel for Climate Change, who considers pro-environmental behavior change, such as change towards less meat-based diets, as a critical lever for mitigating climate change. On the other hand, while recognizing the importance of pro-environmental behavior, the current integrated assessment models that inform the work of the Intergovernmental Panel for Climate Change does not represent a behavior change in what we call an endogenous way. And what do I mean with endogenous? That's very mysterious, and that's nerd talk. The translation for that is most integrated assessment models that talk about human behavior say, we assume that people will start eating a little less meat linearly over the next couple of decades, no matter what. That's one scenario. The other is people will eat more food in total and more meat as a share of their diet as the GDP per capita increases. All of them are external narratives that get pushed into these models. And none of these behaviors get adjusted when we see the climate change or the economy change or my personal health change. And so that's a visual representation of what I just said. Current models say total food demand and animal products demand depend on GDP per capita. If GDP per capita increases, demand increases. What we're doing in this EU project is we're trying to tell a more differentiated story where we make meat consumption and total food consumption depend also on economic factors, because it is an important driver, but also on other factors. And we're doing that by following this recipe of what I said, system dynamics is a happy marriage of qualitative and quantitative research. We started with a qualitative model that was based on a review of behavioral theories and frameworks, on scientific articles and the literature and the published literature, but also, and importantly, on participatory modeling workshops to elicit people's lived experiences with meat consumption or with the decision to transitioning towards less meat-based diets. So we're integrating and synthesizing different sources of evidence to arrive at an understanding of what the main processes are that drive meat consumption, so that we can then translate these into a quantitative model. And that's a visualization of this. So we have theories that are more on the one hand, informed by environmental psychology, but also socio-cultural theories that put the individual in context of a system of practice surrounding them and surrounding their decisions. And we have these participatory workshops where we worked with various groups of people to understand their lived experience. Visually, that then looks like this, or not. Why does this not work? Okay, why is this now not working anymore?
Trying to put this on.
It doesn't do anything.
No, it's frozen. New slideshow. Do we have any slideshow experts in the room?
The entire thing is frozen. What?
Yeah. Should we try closing?
Yeah, please do. Aha.
It's going. Oh, well, I'll let you go.
Yeah.
I just want to make sure it doesn't sound.
There we go. Okay, so visually, this looks like this. I showed you this. I showed you. Now you can't see my cursor anymore. There it is. Okay,
Yeah.
I showed you this where food consumption is only a function of GDP per capita, and this is the magical map resulting from a review of theories of literature and talking to people. I've zoomed out a little. I'm not going to go into detail about what's happening here, but what you see is that we don't have open chains of cause and effect relationships anymore. We have a lot of feedback loops that tell different kinds of stories. They tell economic stories that are related to the ease of access of different types of food, of the ability to substitute different types of food. But we also have sociocultural processes that talk about socialization and internalizing the cultural value of meat. And then we have social ecological processes that talk about how concerned I am about the climate and how much I relate changes in climate to meat consumption, how concerned I am about my health, and how much I relate that concern to meat consumption and climate urgency. There you go. So what I'm showing you here is mainly these three elements of the system dynamics approach. Here, what we have on this map is a representation of feedback loops. We have all these circles where things come back and haunt themselves. We have what we call a system structure, where we see the variables mapped out and their interconnections. And what we have in these boxes here are the levels where information gets accumulated over time, which is information that we need if we want to simulate these models. So this behavior change modeling framework, that's where the term comes from, is embedded in a bigger integrated assessment model where it takes information from land use and agriculture, from climate, from demographics, and from the economy. And it doesn't just take information from there, it also feeds information back. This is a huge project. This is the interdisciplinary project that I've seen in my life. That's climate scientists working on the climate module, agronomists working on the land use and agriculture module, and so on. We can talk about that too, but let's not get ahead of ourselves. So for the behavior change module, this model is partly calibrated to as much data as possible. And what I mean with that is we try to estimate parameters that we're uncertain of so that the simulation results match the available data for as many indicators as possible. And we have a lot of production and consumption related indicators that we could use for partial model calibration. And then Jeff did all kind of magic to run what he calls run ensembles. We never show one simulation run because this is a lot. We have a lot of what we call soft variables here: risk perception, cultural norms. So there's inherent uncertainty, right? And there's also uncertainty because there's a whole huge rest of the model tied to this one here. So we don't show one simulation run and claim that we know the truth. We always show ensembles of 100 runs in a plausible parameter space. And that looks then like the next slide. This is a representation of the modeling and simulation feature of system dynamics. So actually, I shouldn't show this because that's not, well, yes, that's also an uncertainty run, but it's for the historical time period. So we don't see a lot of variation. What we see is 3 different lines. We see red dots. That's the data that we have. Then we have a black line that's helpfully labeled EMB default run. EMB, we're told, is a very intuitive term for endogenous model behavior. That's the beauty of interdisciplinarity. And we have a blue line, that's a GDP-driven default run. That's a model configuration where food demand and animal products demand is exclusively driven by GDP. Both model versions for the historical time period generate fairly similar behavior. And I would say just visually, the match between data and simulation is okay. So either we cheated well or Jeff is really as brilliant as he is. I'm opting to believe that Jeff is brilliant. So then we simulate this into the future. Again, the blue is the GDP-driven median, and the black lines are our endogenous model behavior runs, or the ensemble. So we see that over time, the uncertainty space gets a little bigger. That's obvious. We look further into the future. But what we also see is that not every indicator behaves the same when it comes to these 2 model configurations, right? So the one where meat demand is exogenously driven, and one where we represent human behavior in somewhat more detail. So, for example, the biggest difference may be that we see average daily food demand in an only income-driven model rises to more than 4,000 calories per person per day later in the future. I'm told that in Australia, I should use kilojoules. I can't. I'm sorry. It's a factor of something. But it's a little more than I think is healthy. It's a little much more than I think is healthy. Whereas we see a stagnation of average daily food demand in the more endogenous model behavior. What we also see is that in this uncertainty space, there are some runs that increase food demand again over time. And that's a whole story of how model structure drives model behavior. Generally, what we see here are over time, initially we see an increase, still somewhat of an increase in daily food demand. Then there is stagnation, and then there's a potential of a rebound effect. So there are three different behavior patterns. The first one, a slight increase, is related to rising per capita incomes that kind of finish the first nutrition transition. That doesn't necessarily apply to countries such as Australia or Norway, but other countries where rising incomes will increase food consumption and meat consumption. Then we start seeing that the rising income effect tapers off, and there are some concerns. There are health concerns, environmental concerns that limit or slow down this increase in food demand. And these concerns, they can fade away. Because at some point you're used to the climate being crazy, right? And so in these runs, we can see a rebound effect. This is so far into the future that we don't need to talk about the exact quantitative measures, but it's an example of structure driving behavior. And that's shown here. And it actually does have an effect, not just on food consumption, but on important emission scenarios. That we don't see a huge effect on changes in global surface temperature anomaly and global sea level anomaly might be due to the fact that transportation and electricity use is still just only GDP driven in this model version. So I need you to stay tuned on the final values for temperature change and global sea anomaly. And now I've talked a lot about integrated assessment models and meat consumption. Why on earth did I do that? Well, first of all, because I love talking about it, but I wanted to talk you through this case study to show you that we can use these simulation models to investigate whether our recommendations or insights change as a function of what we decide, how we decide to look at the world. So do we decide to look at the world as being purely GDP driven, or as being driven by a set of interacting processes? Going to hop over the nutrition transitions. We saw that we talked a little about that. And here in this case study, really the approach of looking at identifying the feedback loops, formalizing the structures, integrating different sources of evidence, but also different disciplines, is really what turned out to be really important, because we were able to provide this integrated perspective and to closing relevant feedback loops. But also you saw that we were including stuff like culture or concerns. And that's something that system dynamics can do. There are ways of modeling these so-called soft variables. That also means we need to talk more about uncertainty analysis. Because yes, you can quantify it, you can formalize it, but of course it's inherently uncertain. If you're dying to explore this model more, there is an interactive version that is published on the net, and that does not just contain the behavior change model, but the entire integrated assessment model. There we go. Good. Case study 2. I probably have Miranda. Good, good. I will have to talk about this in 5 minutes so that I can do the wrap up also in 5 minutes. Case study 2 is we're going away from a global analysis to a very local analysis, and we're looking into resilience planning for food security in Guatemala, the home country of one of my previous PhD candidates, Hugo Herrera. Why were we interested in food security and resilience planning in Guatemala? Well, the reason is that Guatemala is in many ways leading the statistics for many bad reasons, right? So we see a very stubborn increase and what's that thing called when it doesn't go away? Stagnation of food insecurity in the country, which on its own is bad enough, but then on top of there being a very high share of the population that lives in moderate or severe food insecurity, we also have climate change that affects Guatemala quite a bit. So what we did in this case study is we looked into what determines the resilience of this food system to climate change, or how can we increase the resilience of food availability to climate change, specifically to droughts. What Hugo did was he did something that we call a group model building process, where he worked a lot with a diverse set of local, regional, and national stakeholders in Guatemala, and built a computer simulation model in a sequence of behind-the-desk activities, individual interviews, and group model building workshops. And he came up with this beautiful diagram that for people like me are very beautiful and intuitive, and for you, probably at best, transparent. What this diagram here does is it tells a story about processes happening. Where is my cursor? Well, gray in the gray box, processes happening on household level, processes happening on the maize market, and then processes happening in the natural system, mainly related to water and nutrient dynamics. And all of these are interconnected. So again, here we have a system where we cut across disciplinary boundaries. We cut across social, economic, and ecological systems, and we look at how the interplay of these systems, how they generate behavior over time for important indicators. And now I said, in this case, we looked into the resilience of food security. And what we mean with resilience is that we looked into how much of a disturbance the system can tolerate before it either, I really so badly want my cursor back, before it either bends from a baseline trajectory, and how much more it can tolerate before it completely breaks. Right, so there are kind of two tipping points in this system. How much of a drought? How much of a drought can I tolerate before I see a change in food provision? And then how much more of a drought can I? But then it will bounce back. And how much more of a drought can I tolerate before it never bounces back? So what Hugo did was he calibrated this model to two case studies. The upper one I keep referring to as the unspeakable one, and the lower one, that one I can pronounce Jutiapa. And what we see here visually displayed for the two case studies is we see these we see these two bars with different colors, where black is the reduction in rainfall that the system tolerates before we see a change in food provision. In this specific case, we can tolerate a 28% reduction in rainfall before we see a change. And then a little more before the system collapses and transforms into a different trajectory. Interestingly, the first case study tolerates a little more reduction in rainfall before we see a change, but then it really has a very small window of opportunity, right? Before it completely transforms. And why is that? Well, this is where the structure drives behavior mantra comes in. The two case studies differ in whether they have whether farmers have access to some small livestock that helps them buffer reductions in harvest due to droughts, and thus spend some money to purchase the missing foods. You can then use this model, and that's a policy analysis part, to experiment with different interventions and seeing what might possibly increase resilience more or less. And so we have the same visualizations here. Black is the stability domain. Then we have the adaptation domain before we move into the transformation domain. And what we see is that different policy options have different potential for moving these frontiers. And again, the reason why the different policy options differ in their effectiveness is because of the structure in the case studies. One of the interventions that worked really well is investing in maize reserves that builds a buffer stock. And the other one again is investing in small livestock. So I'm gonna leave. Oh yes, why did I talk about this case study? Now I start getting nervous for Miranda's hand, but I will still talk about this. Also here, I think you saw that we used the method as a tool to support interdisciplinary research, or to combine insights from different disciplines into a tool that can be used for policy analysis and design. Here, as well as in the first case study, we see how the feedback structure causes the behavior over time in the indicators that we're interested in, and we see the importance of tipping points. I'm gonna leave all of this a mystery for now, more on the method, and I will jump to some overall reflections on using system dynamics in general and in interdisciplinary environmental societal challenges in specific. I believe one of the strong features of the approach is that it has a lot of potential to support the science policy interface. For one, because it has a very strong visual component and interactive features. I didn't show you the math, but it's really not difficult math. So we see the drivers and their interconnections of these systems, the way that they are also represented in the model. And I mentioned that we had interactive versions of the models to allow people to experiment with different assumptions or with different ideas for interventions. The first case study is part of the 7th assessment cycle of the Intergovernmental Panel of Climate Change. The second case study was used by the people who were involved in the group model building process to lobby for policy change, and they actually did get the policy change implemented. So there are some success stories here. What can we in general say about what system dynamics can do and cannot do? And I'm still using this order of strengths and weaknesses, although my daughter said that I had to start with the negative points because people only remember the last thing you say. She learned that at school and I thought it was really, really good, but my logic doesn't work if I start with the negatives. So I'm going to defy her recommendation. What can the approach what kind of activities can the approach support? I'd say system dynamics is really useful for scenario analysis. And the scenario can be, do I include or exclude endogenous behavior change when exploring climate mitigation strategies? It helps you make this decision. But of course, scenario also means what are plausible alternative futures, and how might the system evolve in alternative futures. With the ability of playing with different interventions, with different policies, we can not only assess the relative effectiveness of different interventions, but we can also look into the timing and sequencing of interventions. We simulate over time, so we can experiment with when to start and what to prioritize at which point in time. In my experience, system dynamics can be very useful in inter and transdisciplinary projects in two ways. It helps us integrate and synthesize knowledge across disciplines and policy sectors. And also it helps us facilitate shared understanding, especially when we sit together and develop these maps as a group. What the approach is really not good at is point predictions. You see, especially because we cut across disciplines, etc., uncertainty is real. And we're really more interested in behavior trajectories and behavior modes and not into point predictions. That also means we're better at looking into strategic issues rather than day-to-day operations. Power and justice are chronically difficult to include in the models. I'd argue that they're that we should get better at including them in the modeling process. So it's not completely impossible, but it's really difficult to include power and justice dimensions in the model themselves. And I said it was really nice. The system dynamics was really useful in interdisciplinary projects. It can also really suck because it's so transparent and everybody says, oh, but that's not rigorous science. And that struggle is also real. You make your assumptions transparent and thus open for criticism. Maybe this is not a plus or a minus, my last point, but it's based on experience. Many modelers, especially quantitative modelers, are really bad at implementation and communication. So it's very important to team up with others from the start and actually live interdisciplinarity. And I'm ending with saying that, yes, we love our models, but modeling is really never just about models. The model is one tool, it's an outcome, but the modeling process is what really counts. And I think that's what we have to emphasize more and better. And with that, thank you.
Thank you so much, Birgit. I've had the privilege of having many conversations over the past few weeks with you, but yeah, fantastic to hear about all that work and where it's had policy success as well. Now I'd like to invite Associate Professor Jen Brown up. Jen is an Associate Professor with the Institute for Health Transformation at Deakin, where she works with the Miranda Health Research Mob, which is the Faculty of Health's first dedicated Aboriginal and Torres Strait Islander health research team. She leads a nationally recognised program of research on the commercial determinants of Indigenous health, combining systems thinking, qualitative, quantitative, and policy analysis methods to generate evidence for structural change. Her interest in systems thinking has developed across successive research programs, from research with Aboriginal practitioners on the value of group model building, to applying these research methods with 6 Victorian Aboriginal community-controlled health organisations to develop an Aboriginal-led food policy agenda, to a current national program on commercial determinants of Indigenous health. Welcome, Jen.
Firstly, I'd like to also acknowledge and pay my respects to the traditional owners of the land we're all meeting on and the various lands of the people dialing in. Thank you for inviting me to be the discussant today. Careful what you wish for. And thank you, Birgit, for a wonderful presentation. And I've had the privilege of being part of your masterclass over the last few weeks. So thank you for teaching me how to dance with systems. I still feel like I have 2 left feet in that respect, but I'm learning. On reflection on the talk today and my work and the Science and Society, as this group's named, I suppose there's a lot to feel overwhelmed and depressed about in today's society. We have many, many complex problems to tackle, whether we're thinking about health, environment, social issues. Any of our disciplines, I'm sure, have complex problems to tackle. And at the same time, we're structured into silos academically, politically. Increasingly, we're increasingly divided and polarized, and we currently are experiencing the rise of populism in our politics. As Birgit said, everyone has their own pet theory. So how do we choose what's right? So I'm interested in the discussion that follows about how this approach, how systems thinking and system dynamics modelling can help us overcome some of those challenges, both in terms of the problems that we face and the way we've structured ourselves to be divided. As researchers, our end goal is always to make a positive change in people's lives, for policy, for practice, depending on our discipline. But I know from where I come from in public health, there's a huge gap in terms of evidence and policy. So again, how can we use approaches like this and how can we better work together to change hearts and minds? And maybe that's the marrying of the qualitative and the quantitative, the hard science, so to speak, and the lived experience to provide rational arguments to those who value that kind of reasoning, or to tell people's stories of people's lived reality to appeal to values and to people's hearts. So again, I'm intrigued by these approaches in ways that we can do this all in one project. I'm interested to know from Birgit and from others in the room and online, which global and social problems are best suited, and Birgit touched on some of this in the last slide, to this kind of approach. There are so many probably to choose from. I'm wondering if Birgit or others are thinking, when they watch the news and hear about all the doom and gloom in the world and the problems we're trying to tackle, if you're thinking, this needs a system dynamics model, and then would solve it. We're often at war paradigmatically as well. Quantitative and qualitative methods. Birgit talked about not being rigorous science. I'm wondering if this is a way to overcome those paradigm wars as well, and where a qualitative workshop and a population quantitative survey have equal value in solving some of these problems. And as Birgit said, to create a shared understanding. Something I'm interested in some of this multidisciplinary work with the case studies presented is the issue of policy incoherence. I think the food system is a perfect case study of where we have policy incoherence, where we have different policy goals from different sectors of society or departments of government. Our goals in public health are often very different to the goals of agriculture, to the goals of the food industry, and by extension, business and economic development. And then for environmental and sustainability goals, animal justice, animal rights goals. So if we're mapping all aspects of the system, whose goals are we achieving? And can we achieve everyone's goals through this process? I guess there's always going to be winners and losers in any decision. I'm also interested in the multidisciplinary approaches. I was trying to jot down all the different disciplines Birgit mentioned. I heard psychology, I heard economics, I heard computer science, climate science. I'm wondering, and yet we're structured in our faculties and our schools and our departments with similar people of similar backgrounds. And I know obviously that's something that this network is trying to break down, but what would be the ideal makeup of a team to tackle some of these problems using a systems thinking and simulation modelling approach? It seems like many great minds are needed to come together, and I'm interested to know what the ideal mix would be. And coming back to the title of, I didn't get the exact words down, but supporting the science policy society interface, which is what we're trying to do by using our research to change hearts and minds, both in society and for policy makers. I was the story at the end about how the participants in some of those participatory workshops used that experience to advocate for policy change that was ultimately successful. If that's the kind of outcome that can be achieved from this approach, I think it's definitely something we should all be pursuing. And I think, as Birgit said, the ultimate challenge is we can do our research, but how do we communicate it effectively to the right people, the right audiences, using the right methods to get that change to happen? So I might leave my ramblings there, but hopefully that stimulates some interesting discussion.
Thanks, Jen. There was a fantastic reflections, and I'm very much hoping that Birgit's going to respond to those. If not, I'll prompt you again. Next, I'd like to invite Dr. Tari Forrester-Bowling. Tari is an interdisciplinary, important word, public health researcher specialising in participatory systems approaches to complex health and environmental challenges. She's led co-design and systems mapping initiatives across mental health, alcohol and other drug services, also maternal and child health and healthy food environments. She is also interested in the responsible integration of AI-assisted methods in complex public health research. Drawing on over 20 years of cross-sector experience, spanning local and state government, private enterprise and international development, Tari brings a practice-oriented lens on using systems thinking across research, policy and implementation contexts. Welcome, Tari.
I do love a good bio that makes you go, who's she talking about? So firstly, I was tapping away and my thoughts are all over the place. But one of the things that you were talking about, and I think your case studies really showed them quite well, is that policy link, like what happens next. Often, and certainly I've been in this boat, you do your group model building, you come up with your, these are your leverage points, People have come up with action ideas, and then that's kind of where it ends. And I think, it's, I'm all for the modelling. I love it. But it's not sufficient in of itself if we don't have that political will, the trust and the time, which are all co-requisites. So I guess I'd be really interested in how do you start out with that so that you've got it going along, or do you identify what your leverage points are, and how that could feed into policy, and then how do you present it? Because I feel also that certainly when I'm trying to explain causal loop diagrams or a stock and flow model, it's not an easy sell if you're trying to look at it from a policy briefing paper. How do we get that across without losing the richness that goes into these models? That's something I'm always asking myself, and I think, I'd love to see how it was presented to decision makers, and how did they, especially if they weren't part of the process, which many of the decision makers aren't. They might send somebody off from the department, but how do you present it in a way that gets them to understand what's in that model? Why is it so important? And when you showed the two different structures of the meat consumption, the first one, that very much linear cause and effect, GDP as a driver and an output, very visible down the bottom. When you presented the causal loop diagram, or the stock and flow model, with all of those feedbacks, I was sort of looking around going like, where's the GDP? It's in there somewhere. And it is in there, but it is not the be all and end all. It is a part of the system. And I find that system thinking and system dynamics modelling is so good at being able to incorporate that multidisciplinary approach and ideas, which is one of the reasons I love it. Took me a while to realise I was an interdisciplinary person, like about 3 different career changes and university degrees, and a very large tech debt later. One is also when we have those, when we have our model and we've identified some leverage points, who is really getting to decide where we then intervene? So we then come back to it's still very much a power dynamic. And certainly when we go into doing group model building, one of the things we're always trying to do is be aware of those power dynamics and mitigate them so everybody's voice is heard. However, when we then get to the potential leverage points, do we then have the issue of coming back to the loudest voice or the biggest lobby group? Is there a way to mitigate that that doesn't require changing our entire political system? Because that's probably a boundary object that we can't quite do. And then also, I guess one of my other thoughts was, if that policy uptake is weak, we've gone through all of these community workshops, and we've got all these different specialists from different areas, and everyone's inputted, and we've got our leverage points, we've got, what needs to happen. But if that policy uptake is still really weak, does that then mean that we've got a modelling failure or a political, I don't know what you call it, a political economy problem, a problem with our politicians. So then, does that then erode confidence in this, in modelling, in system dynamics modelling as a method? And there was something around method that I thought of, and then I've forgotten what I was going to say about that. That's all right, fun. My notes. I don't know. I've gone off topic. I guess around how the way that you'd framed the stability, adaptation, transformation. Looking at that, I've never seen it presented. I rarely see it presented, but I've never seen it presented in that way. And I'm just wondering, how can we sort of use that in our context for policy responses when we're talking about emergency food relief, welfare payments, et cetera, while we've got sort of, I guess, those structural drivers such as land rights, land access, market access, chronic underfunding, when those sort of structural drivers are still going unaddressed. Yeah. How's my time going? Yeah. So I guess one of my closing, actually on the interdisciplinary challenge, I do often wonder if within Australia are we making it even harder with our funding structure? So we've got the NHMRC, and then we've got, ARC, and then whatever. So the funding is really set up, I feel, to divide. Even though they all want it to be interdisciplinary, it's very much interdisciplinary within your field area. And I think that that poses a problem for us in Australia to really get that disciplinary depth in, cross-boundary work. No, I won't. Don't worry about that. I guess one of the things, are we looking also towards better modelling or a better sales pitch of systems thinking and system dynamics modelling? How can we improve that interface itself, both the physical interface that some of the simulation models have, but also getting that message across and selling it? So, one of the things that Birgit was saying was it's not robust science or something like that. Because definitely I'm very much I love the transparency that the modelling provides. And there does seem to be here in Australia a bit of a push against transparency around modelling and what's gone into it and what's not gone into it and how the decisions then made. Because I feel like it's often said that that's too much information, people won't understand it. But maybe we need to reframe that. How do we make it easier to understand? I don't know. Thanks.
Thank you, Tari. I'd now like to invite Birgit up to respond to Jen and Tari's reflections, and then we'll open up for Q&A for the room and online. Just a reminder, if you are online, please put questions in the chat.
Wow, Jen and Tari, thank you so much. I so badly want to answer or be able to answer all your questions. I think if I was, we wouldn't be sitting here. We would all be sitting in our garden chairs, sipping lemonade and enjoying the fact that everybody is using systems approaches to change the world for the better. So I'll try my best, but I will have to disappoint you on many of these. And maybe you'll have to help me. I took 3 pages of notes, but I can't remember everything that you said. Okay, so Jen, you started with a bang. How to use these approaches to close the gap between evidence and policy? I think I'll have to take a pass on this one or return. I will hopefully come back to this a little later, but that's the hardest to start with. Nice, better or easier, not better, sorry. Which problems are best suited to be addressed by the approach? I did show a slide with what kinds of questions we can tackle with the approach, but I think a generic but also specific answer is it has to be a dynamic problem. So it has to be something that changes over time. And that something that changes over time doesn't only have to be problematic. We can all agree that a lot of things are problematic, but it also has to be puzzling. And with puzzling, I mean, people need to have given this a lot of thought. And there needs to be a history of well-intentioned interventions, and still we're not there, right? So that then we're in the domain of where dynamic simulation modeling can help. It has to be something that evolves over time and that is problematic and puzzling. What that something is, whether it's a more climate-related issue of one kind or the other, whether it's a health-related issue or an economic one, it's an approach. It's a tool that lends itself to the study of dynamic, persistent, and puzzling problems, and that's where interdisciplinarity comes in. It's a tool that you can use to study issues that you are concerned with. And with you, I don't mean you, Jen, but you as a group, as a community of practice, or as an organization, whatever it is. So it's a tool. It's discipline agnostic. It's more the kinds of the question is what kinds of questions it lends itself to. I think there was something similar, but well, I'll just go through them one in the order that I took notes, or it will be even messier. I'm going to bundle. No, actually, yeah. You say you also asked which great minds or disciplines should we bring together so that we can tackle these issues effectively. And I would say that it depends. It depends on the problem. It depends on the problem on the one hand, but also on the purpose. What's a purpose? I mean, I'm going to focus just on quantitative modeling. In quantitative modeling, we differentiate between different purposes. Our purpose can be to understand, and that's just to understand why things are going the way they're going. It can be to explore. It can and it can be to try and solve. This can be separate. They can be sequenced. It can be about implementation. So it really depends on the purpose. But then how do you, once you have a problem and a purpose, how do you change the relevant disciplines? Good question. Modeling is iterative. Modeling is inherently iterative. So I would say, just get started. And you understand, and you quickly understand where your gaps are. in modeling, that's where you make the heroic assumptions, or where you're like, I don't even know what people's priorities and objectives are. That's a great indication that you're not representing everybody who needs to have a say, who needs to have a voice in the system. Once you try to integrate this, you understand what disciplines you lack to understand how people make decisions, or how the decisions unfold and have consequences in the environmental, economic, and social domain. So we'll probably get a pretty big party pretty quickly. I wouldn't be too worried about not having enough minds around the table, and probably more. And that brings me to, I think, the interdisciplinarity is, I think, not just important, but also it can also be very beautiful. But boy, is it challenging. And it only works if the people who are part of your interdisciplinary, whatever it is, project, team, endeavor, if they're curious. Otherwise, it doesn't work. Otherwise, it's a typical EU project where everybody does whatever they have always done in their different work packages. That's not interdisciplinarity. That's just different disciplines working side by side. For interdisciplinarity to happen, you need genuine curiosity, because I, as a quantitative modeler, will have to understand all these fancy words that hardcore social scientists use, and they package it in beautiful theories and in terminology that make my toenails curl upward. But so I have to be able to overcome this and say, but I want to understand. I see value in what you in what you're doing. I want to explore how we can team up here. That's important in my eyes. That's important in terms of interdisciplinarity. And the other thing, I'm hopping to one of your questions or comments, Tari, is funding structure in Australia and whether it isn't set up to divide rather than to foster interdisciplinarity. I'm not Australian. I've been having the time of my life for 2 months. I wouldn't dare to comment on this, but I want to comment on a higher level issue. And I think, interdisciplinarity again is important, but also it's only useful when it's based on disciplinary expertise. And interdisciplinarity doesn't mean I'm a little bit of a psychologist, a little bit of a climate modeler, and I'm also an agronomist. And I'm going to tell everybody with confidence what they have to do in their disciplines. So it's a dance between having people who know almost everything about almost nothing, and the integrators who try to look at different aspects and facilitate the conversation with the other people who also know a lot about another very little thing. Can we use this as an answer to how to overcome divides between qual and quant? How do we overcome divides between qual and quant? That, to me, that's again a lot a question of curiosity. You have different approaches, and I see a lot kind of contempt for the other approach. They're simplifying. The modelers are simplifying. Oh, the qual people, they're making things unnecessarily complicated. That will never get us anywhere. This attitude will never get us anywhere. Both have merit. Both answer different questions. And again, we need to find ways of seeing the value in having these different perspectives. And I'm not saying all of them have to be integrated into a model. That's why I ended with saying it's never just about the model. It's about the process. The model is just a tiny little artifact. that includes and contains some elements, but there are all these rich stories from the people who were involved in the modeling process, who had a lot more to say than what we see manifested in the model. And these stories are important. These stories are important as a disclaimer of what's happening in the model, but also as a context to understand what's happening or what we're saying is coming out of the modeling process in terms of insights or recommendations. So you see, I'm originally Swiss, so I'm very much a bridge builder, and I'm neutral. I'm trying to facilitate conversations between different perspectives, and Miranda wants me to focus on other things.
I just want to make sure you have time for questions.
Yeah. Let's see. How do we change minds and hearts? That's I think that's. I kind of heard that from both of you, Jen and Tari. It's great if we have success stories. How can we make every project a success? I think some projects are really great to see because they had the stars were aligned. You had champions in the organization who would bring this up to decision makers and use their own terminology to convince policymakers. So for some projects, the stars are aligned because actually something is happening. I don't have the secret sauce for scaling this up. And I think that's one of the challenges, right? We can make it work, but how can we make it work at scale? Because there is no secret sauce. There is no silver bullet solution for complex systems. So we always need to patch together different elements of success and adjust and tailor the approach to different contexts. Yes, and so on. I still have more answers for Tari, but we can get back there.
I'm sure that might come up in some questions. Does anyone have any questions for Birgit in the room first?
I have an online one to busy typing.
Okay.
So I'll come back to it.
Someone's busy typing online. Anyone in the room? I will ask, it's that process question, which is so hard, about if you've got the quantitative folk broadly and the qualitative folk, and you're trying to incorporate a variable like culture into a model. Can you just talk a bit through what does that kind of teasing out negotiation process actually look like?
Well, I would say, again, it's never just about the model. And so we touched a little on power dynamics and justice issues. So, it's really also very much a question of how you design the entire process. How do you map your stakeholders? We modelers are terribly bad at this. How do we talk to stakeholders? We're chronically bad at this too. So it's not so much, it's really about how do we assemble not just a team, but a process that makes sure that important voices are heard. And if they're not heard the first time around, that they're heard the second time around. And that what comes out of these discussions is taken up either by the model itself or by the narrative spun around model communication. And do we need a better sales pitch, Tari? Oh, yes. Yes, very much. And yeah, so I think, this being such an interdisciplinary approach, building some bridges. We had one participant in our modeling masterclass who at some point was very depressed, saying, so I need to be able to do everything. It's really teamwork. It's really teamwork. You can't do it all yourself. Yes.
I have two questions. One is from me, and one is from Ben Federick, one of our former grant holders online. But his question got cut off. So Ben, if you can hear me, please finish your question. So I'll start with a question from me, if that's okay, which is that you speak about being discipline agnostic, and I'm thinking about how one runs a project like this and the kind of leadership qualities it takes to be. I'm assuming there's normally one leader. No, it's a team project from the very beginning. I'm really interested in that dynamic and what kind of qualities, and how do you teach that and promote that and mentor that and grow that? Because everyone's encouraging interdisciplinarity, of course we are, but we know that it takes something special and different to be able to really do that work. I'm interested in those qualities.
Yeah. Okay, I'm going to use this one question to shamelessly advertise the master program in system dynamics at the University of Bergen. I never mentioned it so far, so thank you for that. How do you teach interdisciplinarity? To me, it's the same as teaching system dynamics. It's in a way very simple and also so complicated. I mean, I gave you the theory of system dynamics on slide 2. Feedback loops and stocks and flows. That's the theory. That's it. The rest is doing it. You learn how to model by modeling, and by modeling over and over and over again, preferably in different projects with different purposes in different setups. And that's what we do in our master program, where the only admission requirement is that you have a bachelor's degree. In what your bachelor is in doesn't really matter. And so we get students, from biology, sociology, engineering, all the way to philosophy. So while learning or while iterating on the modeling itself, they get thrown together, for better or worse, in this cohort, where they, in order to work as a group, have to learn how to communicate with people from a different disciplinary background, but also from a different cultural background. And by doing this over extended periods of time, you start becoming it, right? You start living it. I think that's the only...
Communication. Can I ask a question? So Ben Henrik is saying, thanks, Birgit. I'm using serious games for climate adaptation. Ben develops these amazing games that help people do climate modeling, tabletop games. He said, could you expand on your idea that you don't manage but dance with complex systems? What it might mean for well, he said, I'm interested as my research is starting to expand into systems actors and cross-scale sites from local to national. So it's still climate adaptation, but he's trying to understand the logic of not managing but dancing, and maybe what that could mean for someone who's trying to move across sites, I guess, from local to national climate adaptation. They're not about to do justice.
Not to minute answer. 2-minute answer.
Okay, and the 2-minute answer. So first of all, dancing with systems is a quote by the biggest system dynamicists ever. Anyway, that's by Donella Meadows. And what I mean with it is maybe I'll illustrate it with the story that I told you about this potential trajectory of meat demand increasing, stagnating, and then potentially bouncing back. What I mean with not managing but dancing with systems is you can't say, okay, let's introduce a meat tax and then solve the problem once and for all. The system will hit back. People will get used to the tax, they will change their behavior, and you never know. So you will have to stay alert and adjust to changes in circumstances and conditions. You have to dance. You can't just hop and then say, I landed. And I mean, I don't have a 30-second answer on how we can translate this to local, regional, national, and global climate adaptation. Ben, I'm very sorry. I have to disappoint you on this.
You got off there. I'd like to thank Birgit so much for coming to speak to us today. We're so lucky to have your wealth of expertise, and also like to thank Jen and Tari for your excellent reflections. I thought that really added to my understanding of the discussion today as well. Please keep your eye out for our next SSN seminar, which will be advertising soon, I'm sure. And thank you for joining us in the room and online.
Yeah.